So far, you've seen how to visualize one or two variables. But what happens with more than two variables? Here are the plots of life expectancy using the UN dataset. You've visualized life expectancy against length of schooling and GNI per capita separately. What if you wanted to see the effect of both variables on life expectancy together? The obvious answer is to draw a 3D scatter plot. Unfortunately, that's a terrible idea. With a three-dimensional object on a two-dimensional screen, you lose all sense of perspective, and it's difficult to interpret. Sometimes, drawing the plot at different angles can assist interpretation, but most angles are unhelpful. Fortunately, there are other ways of drawing more than two dimensions on a flat screen. For points in the scatter plot, you can represent values using different colors, sizes, levels of transparency, and shape. Here, length of schooling and GNI are shown on the X and Y axes. Then life expectancy is represented on a color axis. Shorter life expectancies are shown in blue, moving through green to yellow for longer life expectancies. The yellow dots are in the top right, meaning that countries with the longest life expectancies have both long schooling times and high GNI. As a bonus, you can see the positive correlation between schooling and GNI. One downside is that you can't see precise values for life expectancy. You can estimate, give or take 5 years, but you couldn't say for definite whether a colour corresponds to 64 years or 65 years. A second option is to change the size of the points, with larger points representing larger numbers. This is okay, but has more problems. Firstly, larger points can seem more important. Sometimes that might be acceptable, but if you want people to concentrate on countries with a low life expectancy, it's a bad choice. Secondly, it's harder to judge precise life expectancies than with colour. Thirdly, the large points tend to overlap, making it difficult to distinguish individual countries. Transparency has similar problems to size. We're naturally drawn towards points with less transparency, and it's difficult to determine precise values. Using different shapes is a fourth possibility. This requires cutting the range of life expectancies into groups. One shape corresponds to life expectancies between 50 and 60, another shape to life expectancies between 60 and 70, and so on. This isn't ideal because shapes have no natural ordering from smallest to largest. For example, a square isn't implicitly greater than a circle. To interpret this plot, you have to memorize which shape corresponds to which age range. This is a big mental burden. One final option is to draw panels for different subsets of the dataset. Like shape, you need to cut the life expectancies into categories. This is nice for determining trends across groups. In the top row, you see that the points in the 60 to 70 group are further right than the 50 to 60 group, indicating more schooling. Comparing the top and bottom rows, you see that, as well as moving right, the points also move upwards, indicating more income. In this variation, each panel contains data for an age range of 5 years rather than 10. This gives you more precision for life expectancy, but it takes up more space, and you spend more time having to move your eyes between panels, making interpreting harder. Line plots also have a choice of aesthetics to use as additional dimensions. Colour is most common, but line thickness and the transparency level are options as well. These behave similarly to points. One new aesthetic is line type. For example, you can draw lines with dashes or dots. Here's the plot of technology adoption in the USA, which uses colour to distinguish lines. Here's an alternative version using line type to distinguish the lines. Unfortunately, even with just 4 lines, it's difficult to distinguish the different types of dashes. Let's move to a higher dimension.
Cherry. Thank you. Thank you for dropping by. Hello, 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 hello. Good evening. Okay. So I'm discussing data visualization. This is how we gather the insights for these platforms. How we gather the data and create the insights. So for the data visualization, I've already finished with the 1 and 2 dimension. Now we're on the multi-dimension. Thank you so much. I have to poke nga pala. Hindi pa ako marunong. Okay, so it says here that if we have a scatter plot, but we want to distinguish the points in some way based on another variable, then you have a few options. So as discussed in the video, 3D plots are usually dreadful on a 2D, two-dimensional screen, but there are other options to stick to a X and Y axis and still visualize the third dimension. So we can change the color, the size, the transparency or shape of the points, or split the plot into multiple panels. So thank you for poking back. So, okay. Here we can see the data set of house prices in Los Angeles, USA that we first encountered in chapter 2. I forgot. So we have to explore the different options for distinguishing points from the 4 cities, then determine which statement is false. So the instructions is, for the instructions, so we have to determine which of the following statements here is the false one. Okay, so using different sizes or transparencies make it hard to distinguish points that overlap. It's true, because here we cannot distinguish which is the graph here. We can only see the dots, but we cannot distinguish the data because the dots are overlapping or the shapes are overlapping. Then, so we have to eliminate the first statement. Then, using separate panels provides the best way to distinguish points from each city, but makes it harder to see if there is a single trend across the whole data set. So let's see. Panels. Okay. So to get a clearer view of the data, the first statement says that using different sizes or transparency. So we have to view it based on the size, okay, and transparencies. So based on the sizes, we cannot see the data because it's overlapping, but with the transparencies, I think it's more, somehow more, we can distinguish the data more, but still it's overlapping. Then with the panels, separate panels. Mhm. It says here that using separate panels provides the best way to distinguish points from each city, but makes it harder to see if there is a single trend across the whole dataset. Yes, it's true. So the third statement, using different shapes provides the best way. Shapes. Using different shapes provides the best way to distinguish points from each city, but makes it harder to see if there is a single trend across. Using different color provides a good way to distinguish points from each city, but lighter colors can be hard to see against the white background. It's true. So using different shapes. Okay. So the answer is distinguished point. There are several different ways of distinguishing points in a scatter plot, but color and separate panels are the most reliable methods, unless you want to spend hours squinting at the plots. Okay. Another dimension for line plots. Now we have to distinguish companies based on these options. So as with points in a scatter plot, we may often want to be able to distinguish several lines in a line plot. Like points, we can change the colors of transparency level or use multiple panels. Another dimension for line plots. Okay. So this is line plot. The two differences to points are that we can change line widths rather than point sizes, and we can change line type rather than point shape. Okay, so the line type are solid dashes or dots rather than a point shape. Then the line plot shows the stock. So the data here shown here is the stock price for the 5 technology companies collectively known as FAAMG, which stands for Facebook, Apple, Amazon, Microsoft, and Google. Okay. So FAAMG is Facebook, Apple, Amazon, Microsoft, and Google. Okay. And the prices have been adjusted for dividends and splits Then scale to be relative to their, okay, then scale to be relative to their highest price over the time period, so they are more easily comparable. So for the instructions, explore different options for distinguishing lines from the 5 companies, then determine which statement is false. So now, what we're doing now is just analyzing. We're doing some analysis to determine which which of the 5 companies, which statement is false based on the data from the 5 companies. Okay, so for the instructions, all 5 companies began 2018 with a higher price than they began in 2017. Began 2018 with a higher price than they began 2017. So this is the data source here is the from the Yahoo Finance. Okay. Where is the legend? Okay, it's followers in Instagram. Okay. So my so in 2018 it's higher. Also here it's higher. It's higher. It's higher. It's higher. So this is true that all companies began 2018 with a higher price than they began in 2017. We're looking for this false statement. Then in 2018, Facebook's stock price decreased by a greater fraction than any of the other companies. In 2018, okay, in 2018, it dropped 2018, not Amazon here. Okay, here in 2019. Hello, Gio. Thank you. have distinguished companies. I think it's hard to distinguish between the color, the color shoes, because the color here is some happy. So it says here that in 2018, Facebook's stock price decreased by a greater fraction than any of the other companies. So Facebook, the Google and Facebook almost have the same color. So I don't. What color is this? Who has the I'm not sure with the second statement, because all of them seems to be I think this is false, because decreased by a greater fraction than any of the other companies, because all of them seem to decrease on that same period of time. Then, from the start of 2019 to the start of 2020, Apple's stock price more than doubled. Apple, Apple, Apple. Okay, it's true. Because from the start of 2019 to 2020, start of 2019, it's in between point 0.4 and point 0.6, so it must be in point 0.5. Then at the end of 2020, it is more than double. Point 2. panel. Let's see the panel. Apple. So, okay. 3 is 0.5. And at the end. All companies began 2020 with a higher price than they had halfway through 2019. Hello, thank you. Can I poke you? Thank you so much. So I think the answer here is yes, but decreased by a greater fraction than any of the other companies. Facebook, 2018. It's because from 0.8 goes down to 0.6. Same with Apple. So I think this is the answer. Is this true? So I wish we could make people up much more. All 5 companies began 2020 with a higher price than they had halfway through 2019. 2020, all of them are higher, except Amazon. So I guess began 2020. Then they have halfway through 2019. Okay, because of Amazon, you can see here that in 2019, halfway 2019, the price is greater than its price when it closes down on 2020. Okay, limitless. Amazon stock price decreased in the second half of 2019, similar to the case of Scatterplat's best. Choices for distinguishing lines are often colors or separate panels. Okay. So
You just saw that the most powerful tool you have for distinguishing data values is often colour. Now you'll see how to choose the best colours for your plot. How you define colours has an impact on which colours you want to choose. Many programming languages define colours by how much red, green and blue the colours contain. So the software knows how bright to make the red, green and blue pixels on screen. We call this the red, green, blue colour space. Graphic designers often define colours by the amount of cyan, magenta, yellow and black they contain, because colour printers have these 4 ink cartridges. Using this colour space gives them the highest fidelity between what is on screen and what is printed. Here's the plot of Los Angeles house prices. There are some problems with the choice of colours. Firstly, yellow points are harder to see than reds, meaning viewers might spend less time looking at the yellows and miss important insights. Secondly, the colours blue and purple are perceptually quite close. That is, they appear to be quite similar. By contrast, yellow appears very different to the other colours. This could lead viewers of the plot to think, possibly subconsciously, that the yellow points are different to the others.
Charmy. Thank you for watching.
The colour space designed for data visualization is called hue, chroma, luminance, or HCL. It's designed to deal with issues of colour perception. Hue is like the colour of the rainbow, from red through orange, green and blue, to purple and back to red. Chroma is the intensity of the colour, from grey to a bright colour. You can go from grey to bright green, or grey to bright magenta, or grey to any other hue. Luminance is the brightness of the colour, from black to white. For example, you can go from black through cyan to white, or black through red to white. When choosing the colours for your plot, you can pick one of three types of colour scale. Qualitative colour scales are used to distinguish unordered categories, and usually involve changing the hue, while keeping chroma and luminance fixed. Here's the technology adoption line plot. The technologies are unordered, since it isn't useful to think of refrigerators as greater than stoves. Each line has a different hue, but constant chroma and luminance. To emphasize ordering in your data, that is, to show that values are greater than or less than each other, you need a sequential color scale. Most sequential scales change either chroma or luminance, while keeping hue fixed. Here's the fruit and vegetable consumption bar plot. The categories are ordered from 0 to greater than 5, so a sequential color scale makes most sense. You can also use sequential scales with continuous variables. Here's the scatter plot of life expectancy. This is slightly cheating because it uses a sequential scale that changes the hue. The color scale is called viridis, and it's designed to be easily viewable by colorblind people, and to print well in black and white. This color scale had a lot of science used in its development. If you make your own sequential scale, it's better to stick to changing only chroma or luminance. To emphasize whether values are greater than or less than some middle value, use a diverging scale. These are similar to sequential scales, but have a neutral color like white or gray in the middle, and have increasingly bold colors with different hues on either edge. Here's another survey dataset on green technology and recycling in Malaysia.
I'm studying.
Each question has a choice of 5 responses, from strongly disagree to strongly agree. Neutral responses form a midpoint, making a diverging scale useful. Here you can see each question on its own row, and the colours get bolder as the opinions get stronger. Let's play with some colours.
Okay. For the eye-catching colors, not all colors are as eye-catching as others. So this can cause a problem for data visualization. Hello, Miss Charmy. Actually, what I'm doing is I'm studying how to visualize the data. All the insights we're seeing from these platforms we're using are a product of the data analysis. So I'm learning data analysis. So it says here that not all colors are as eye-catching as the others. So this can cause a problem for the data visualization because having some data point more obvious than others can be biased and the way we interpret a plot. So unless we specifically want to highlight some points, each data point should be as easy to look at as all the others. So here we can see the data set from the camera trap in Panama. So this time, the speed of the animals they pass the camera is plotted against the time of the day that they were caught on camera. And the agouti have been joined by another rodent, the paca. It's very hard to distinguish. I can only see one rodent here. So each version of the plot contains purple and yellow points, but the other one okay, so but the other one, the purple points are easier to perceive than the yellow points. So based on this graph, which statement is true? I can see it says here that the agouti here has been joined by another rodent, but from the picture I cannot I cannot see if there is if this rodent here has an accompaniment accompany has a company. So we're looking for the true statement. Which statement is true? It says here that to ensure that all data points are equally perceivable, they should all have the same colors, which is false. Because if they all have the same colors, we cannot be able to distinguish one from the other. So to ensure that all data points are equally perceivable, they should have all the same chroma. Aren't color and chroma the same? I'm not sure. Okay. To ensure that all data points are equally perceivable, they should have all the same luminance. To ensure that all data points are equally perceivable, choose a qualitative, sequential, or diverging scale in new chroma luminance color space. To ensure that all data points are equally perceivable, they should have all the same hue. Qualitative, sequential, or diverging scale in new chroma luminance color space. me. So we have to get all the, so the colors we choose for our plots will affect how the plot is interpreted. Using a qualitative, sequential, or diverging scale in a uchromoluminance, color space is almost always the best option. So now for the qualitative, sequential, diverging. Qualitative, sequential, and diverging. Okay. Oh, these are the three types of color scale, each designed to highlight different things in a visualization. The types are qualitative, sequential, and diverging. The purpose is to distinguish unordered categories, to show sequential for to show ordering and order or sequence. Then the diverging is to show above or below a midpoint. So here's the graph. Choose the type of color scale. Okay. It's because, Miss Charmy, it's because we have a different niche. You can sing so well, but I can't. So I'm just doing what I think which is mostly my strength. But anyway, thank you. I hope you can learn something from me. So here we can see the results of a survey about math anxiety from a class of students. Oh, so the graph here is a survey about math anxiety, anxiety on math from a class of students. I guess we really should focus more on teaching the students how to be more on academics. But I don't have anything against but it's just that the kids nowadays they don't have the patience. So I guess it really takes a lot of patience and understanding to learn analysis. But I guess it depends from person to person. So each question has its own row, and responses range from strongly disagree to neutral to strongly agree. Okay. Excuse me. Strongly agree. Disagree, neutral, and agree. Okay. So choose an appropriate color scale for the plot. Okay. Choose an appropriate color scale for the plot. So I think this qualitative is because it displays different colors. You can easily distinguish. Or sequential. Mhm. My mind goes blank and I'm unable to think clearly when I'm doing the math. It is diverging. Thank you for thank you for staying, Miss Charmy. Thank you so much. Actually, uh, I only stream whenever I feel like streaming. Thank you. I told you. How can I ever find you? Appropriate color scale for the plot. Appropriate. I think everything's appropriate except for except here. I think qualitative is okay as long as it has different colors. You can see it clearly. The sequential and diverging. I think the diverging is most suitable. Yay! Divine use of a diverging scale. Diverging scale is appropriate here since the responses have a natural midpoint or neutral. Yes. Actually, it's more on a common sense I'm using because these here the colors are contrasting, so we can easily see the different can easily differentiate. So for the highlighting data, so up to now we focused on using colors and other plot aesthetics to make all data points stand out as much as the others. Usually that's a good idea, but occasionally you want to highlight specific data points. Hello, thank you for staying. Thank you so much. Here's the dataset of the greatest hip hop songs of all time. From chapter 2, songs by two rappers at the center of the 1990s East Coast West Coast hip hop rivalry. The Notorious Big and Tupac are colored differently. I don't know any of them. Center of the 90s. Already, I'm already in high school that time, but I don't know these these rappers. Okay, use the sliders to control the highlighting of songs of these artists via point size, transparency, and chroma. So how many songs for each artist made it onto the critics list? Okay, so we have to use the slider. Set the points. The Notorious Big has 9 and Tupac has 8. Wait, use the sliders to control the highlighting of songs by these artists via point size, transparency, and chroma. Wow. Set the point size for the Notorious Big and Tupac songs. Once again, I don't understand you. The Notorious Big has 9 and Chroma has 8. Getting hungry. This is hard because I don't think I understand. It's very different to analyze when you don't understand the question. Okay, it's two rappers, the Notorious Big and Tupac songs. So transparency of each song. So the Notorious Big, the color is pink, while the Tupac, the color is blue, and others the color is green. So critics score, critics list. How many songs for each artist made it onto the critics list? So can I I do this? Others. Huh. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. Peacock has 8. And this big has 1, 2, 3, 4, 5, 6, 7. Huh. Even when I was wrong, I got my point across. If you make your points bigger or smaller, it can help you get your point across. So,
To visualize many variables, you'll need to use more advanced plot types. Here we'll look at pair plots, correlation heat maps, and parallel coordinates plots. Pair plots work with up to about 10 variables at once, and they show you the distribution of each variable and the relationship between each pair of variables. Here's a pair plot of LA home prices. There are 4 variables in the dataset, giving 4 rows of panels and 4 columns. Let's explore this piece by piece. Panels on the diagonal show distributions of variables. City is a categorical variable, so its distribution is represented as a bar plot of counts for each city. The other 3 variables, number of beds, price, and area, are continuous, so their distributions are represented by histograms. Panels off the diagonal show relationships between pairs of variables. When both variables are continuous, you see scatterplots of each pair of variables and their correlation. For example, in the second column, 4th row, you see a scatterplot of number of beds versus area. In the 4th column, 2nd row, you see that number of beds and area have a positive correlation of 0.782. When comparing a categorical variable to a continuous variable, you get a box plot and a histogram of the continuous variable split by the categorical variable. For example, in the 3rd column, 1st row, you see a box plot of prices for each city. In the 1st column, 3rd row, you see a histogram of the same thing. The histogram is vertical, so the positions match those in the city panel on the diagonal. Pair plots can be tremendously helpful for quickly exploring a new dataset. For the special case where you have many continuous variables, a close relative of the pair plot, called a correlation heat map, is simpler and scales to visualizing even more variables at once. The idea is that you draw a pair plot, only including the panels for correlations, but instead of showing numbers, you show a colour. Correlation heat maps are designed to show relationships between pairs of continuous variables. They're compact, so you can easily compare tens of variables at once. Here's a correlation heat map of a customer satisfaction survey for a Yellow Pages advertising product. Customers rated the importance of product features on a scale from 1 to 10, where two features consistently received similar scores by customers. They are positively correlated and coloured in a more vibrant red. Those bright reds in the bottom left show that the price-related product aspects all strongly correlate with each other. Here's the plot of the United Nations country data again. It showed that you can use colour on a scatter plot to display 3 variables at once. However, with 4 or more variables, scatter plots can quickly become complicated to interpret. Parallel coordinates plots provide a solution to this when you have lots of continuous variables and want to understand their relationship or group them into clusters. Here's a parallel coordinates plot of the 3 variables you saw before, plus the Human Development Index score. Each line represents one country, and each continuous variable appears on the x-axis, just like a bar plot. To make each variable comparable, the y-axis simply ranges from the lowest value in the dataset for that variable to the highest value. Unfortunately, this plot is a mess because the world is complicated. Let's try splitting the dataset by continent. Now some patterns emerge. The South American countries are quite consistent. Their GNIs are low, and their Human Development Index, life expectancy, and schooling values are mostly between the median and 75th percentile. In Europe, you see a wide range of GNIs, but the other metrics are all high. In Africa, the GNIs are all low, but the other metrics show a wide range. The wonderful thing about this plot is that more metrics can just be added to the x-axis. You can easily compare 10 or 20 variables at once. Let's visualize.
Hello, Miss Sarah. Yes, I even though even though I'm already sleepy, I choose to stream today. Thank you so much. Thank you, thank you. Thank you, Miss Charmy and Miss Sarah. So for uh, moving on, we have to interpret peer plots. To get a quick overview of a data set, it's really helpful to draw a plot of the distribution of each variable and the relationship between each pair of variables. So a pair plot displays all these plots together in a matrix of panels. It shows a lot of information at once, so to interpret it, try looking at one panel at a time. So here we can see the Panamanian camera trapped data for the agouti and paca, as well as 3 new species. Coati, okay, Coati, and Picari. So here is the graph. So there are 1, 2, 3, 4, 5 species. So we have to categorize these statements about the pair plots as true or false. Uh-huh. So here there's a strong negative correlation between time of sighting and speed of the animal. Strong negative correlation. Where's the strong negative correlation? Time of sighting and speed of the animal. Per second, speed per second. Strong negative correlation. The animal with the fastest 75th percentile speed on camera was an agouti. Agouti is the 75th percentile speed on camera. Speed. Of course, just have to. There are more than 250 sightings of Peccavi in the dataset. Most animals were traveling at less than 1 minute per second when caught on camera. Less than 1 minute. 1 mile. 1 meter per second. It's 1 meter per second. Then all species were caught on camera most often around dawn and dusk, 6 a.m. and 6 p.m. What's the time of the day? It's here. Between 6 a.m. Kaka is the only nocturnal animal in the dataset. Mali. So it means that here we have to place it here, place it here, place it here, and place it here. Hey. True or false? Okay. It's 82%. I have to. So for the interpreting correlation heat maps, if we want to find this relationship between many pairs of numeric variables, we can use a close relative of the pair plot, namely the correlation heat map. It takes the correlation scores we saw on the pair plot, but rather than giving us lots of numbers to look at, it displays them using colors. A great use case for this is finding related products. Okay. So if you want to find the relationship between many pairs of numeric variables, you can use a close relative to plot, namely the correlation heat map. It takes the correlation scores we saw on the pair plot, but rather than giving us lots of numbers to look at, it displays them using numbers, using colors. Okay, a great use case for this is finding related products. Here's the data set from a survey of Scotch whiskey consumption. Mhm. In the correlation heat map, each row and column shows a brand of Scotch, and cells show that correlation between drinking one brand and drinking another within the past 12 months. So So for the instructions, we have to categorize the statements about the correlation heat map as true or false. So these are the people who drank a singleton were unlikely to drink Shiva Sirgal singleton. Super sweet. Recordation in drinkers of crime of record and drinkers of Shivas Regal. So interpreting coordinates plots. Parallel coordinates plots are designed to help us view the relationship between many continuous variables at once. Here is the dataset of fatty acid levels in olive oil samples from 6 regions in Italy. Each line in the plot represents one oil sample. Since the region is a categorical variable, we have 6 parallel coordinate plots, one in each panel. have to drag the items into the correct bucket once more. Oils from West Liguria in the north have high levels of linolenic acid. West Liguria. This is the linolenic acid. So Sardinia has the coast Sardinia and the inland Sardinia. Oils from both regions in the Sardinia have low levels of eicosanoic acid and high levels of lycophenolic acid. Linoleic acid have low levels of eicosonic. What is eicosonic? Oils from the inland Sardinia in Sardinia have a wide variety of level of oleic acid.
You've seen a lot of plot types so far, but one type has been conspicuously absent. That's the pie plot. It's a wildly popular plot type, but we've been avoiding it for a good reason. Here's the bar plot of famous athletes by sport. If you convert the coordinate system for the plot from Cartesian coordinates, that is, standard x and y axes, to polar coordinates, you get a pie plot. A pie plot is just a bar plot, where the bar lengths are converted to angles. Unfortunately, this plot is much harder to interpret than the bar plot. For example, it's really hard to answer questions that were easy with the bar plot, like how many cricketers were there on the list? Data visualization research suggests that bar plots are almost always easier to interpret than pie plots. So the answer to the question of when should you use polar coordinates is that they're almost never a good idea. There is one exception, though it's fairly niche. If you have data that has some natural circularity to it, like the time of day or a direction, then polar coordinates can be acceptable. Here's a histogram of animal activity from the Panama camera trap dataset. You saw this as part of the pair plot in the previous chapter. It's a great plot with one problem. The activity from the nocturnal packer appears to be split in two, because the plot doesn't recognize that midnight on the left of the x-axis is the same as the midnight on the right of the x-axis. One possible fix is to convert the histograms to polar coordinates, forming a rose plot. This is slightly different to the pie plot because it's the x-axis that's converted to angles, and the bar heights still remain as lengths. Now if you look at the packer's activity distribution, it's clearer that it's one burst of activity lasting all night, rather than two separate bursts. Let's explore some circular plots.
So pie plots, which is sometimes called as pie charts, are extremely popular, but often difficult to interpret. They're just bar plots converted into polar coordinates, and humans are generally worse at perceiving angles accurately compared to lengths. Okay. So following on from the Scotch whiskey dataset in the last chapter, there's another dataset from the Health Survey for England. This time on alcohol consumption in English men aged 16 or more. Then pie segments and bar heights represent percentages of responders. So it's easier that look at the pie plot and the bar plot and determine which statement is true. Hello, hello, Megumi. Thank you once again. All age groups have less than 20% non-drinkers. No, it's less than. No, this says more than, I think so this is false. All age groups had at least 50% of people drinking up to 14 units per week. It's also false. Only the 75 plus age group had more non-drinkers than this is also false. Huh? All age groups had at least 50% of people drinking up to 40. Ah, this one. Ito pala, yung palang up to 14 is the green. Okay, I have a plot. Those plots. One good one good use case for polar coordinates is when the data is naturally circular. For example, when it is a compass direction. If you use a histogram with polar coordinates, you get a rose plot. Okay. Polar coordinates. So here we can see a plot of wind direction data from a meteorological mast. Knowing the predominant wind direction is important for weather modeling and for determining where to site wind turbines. Wind measurements were taken a 10-minute interval over an 8-month period. So this is their direction. So it says here that we have to look at the histogram and rose plot, then determine which statement is true. True. Okay. Distribution of the wind directions has 3 peaks. predominant wind direction were north and southwest. Okay. So for cyclical data, polar coordinates can sometimes make a plot easier to interpret. It's just 30%.
Let's take a look at problems with axes in plots. One thing that's fundamental to bar plots is that the length of each bar is proportional to whatever value it represents. In this infographic found on the wonderful subreddit, Data is Ugly, the 22.5% scored by Yang in the poll appears to be much larger than the 21% scored by Sanders, or Bernie, as he is affectionately referred to here. If we draw the bar plot correctly, you can see that the difference between the two poll scores is fairly small. I don't want to single out Yang specifically, but I would like to warn you to be cautious when interpreting plots on political posters. It isn't just politicians who play fast and loose with the rules of data visualization. This time we have a stacked bar plot from Data is Ugly about market share of phone operating systems. The problem with this is more subtle. Rather than making up bar lengths to look good on a poster, the values do match a real scale. The mistake is that the y-axis, containing market share, begins at 75% instead of 0. This makes it look like Android and iOS have similar market shares. If we draw the stacked bar plot correctly, we see that Android has a much larger share. Another common bad idea for plots is to use two y-axes. This is typically done when you want to plot two things on the y-axis with very different scales. Here you can see the United Nations dataset with length of schooling on the x-axis. The red points are related to life expectancy and linked to the y-axis on the left. The blue points link to the Human Development Index for the country and linked to the y-axis on the right. The two axes are needed here because the life expectancies are all between 50 and 90, but the Human Development Index is on a scale from 0 to 1. The problem is that by changing the right-hand y-axis, the interpretation of the plot changes completely. On the left, it looks like there's a strong correlation between life expectancy and Human Development Index, but on the right, it looks like there's no correlation. You have to stare hard at the numbers on the axis to see what's going on. A much better solution is to admit that you're trying to plot two different things and keep them in separate panels, so it's clear to your audience that they're different metrics. Time to play with some axes.
So, bar plot axis. When we look at a bar plot, we use the relative length of each bar to help interpret what is happening. If we don't include 0 on the axis used for bar lengths, then the relative lengths of bars are distorted, and it is easy to be misled. Okay, so here is the part back of another question from the health survey for England, this time about people with asthma. So we have to compare version of the plot with each y-axis and determine which statement is true. Okay. To 24 have more than twice the percentage of non-asthmatics. And 45 to 54. 45 to 54. The majority of people 35 to 74. 16 to 24 have more than twice the percentage of non-asthmatic than have dual axis. One popular but terrible idea is to draw a scatter plot or line plot with two different y-axes. So this typically happens when we have two matrix with different units and different scales that we want to plot against the common x-axis. The problem is that by changing the relationship between the two axes, we can tell almost any story that we want to with the data. So here we can see the stock prices of Microsoft and Amazon from 2017 to 2020. When we saw this in chapter 3, these prices have been adjusted relative to the maximum for the company. That way, that way each line was comparable. Here, the prices have been adjusted for dividends and splits, but they have not been scaled relative to their maximum. So for the instruction, we have to adjust the vertical position and stiffness of the slope for the Amazon line, then determine which statement is true. Amazon from 2015. Adjust the vertical position and stiffness of the slope for the Amazon line. That determine which Amazon line.
There are two basic measures of how good your data visualization is. The first measure is how many insights can the reader get from your plot. For far too many plots, the answer is 0. In this video, we'll look at some ways to avoid that situation. The second measure is how quickly the reader will get those insights. If your plot is being presented in a meeting, you might reasonably expect your audience to concentrate on your plot for 20 seconds. Often, you need to get your message across quickly. Chart junk refers to anything in the plot that makes it harder for the reader to get insight into the data. We'll look at some common problems in the following slides. One term that's less well known is skeuomorphism. That means adding things that happen in the real world to virtual objects. For example, you could add shadows to bars in a bar plot. Here's an example from the BBC TV network, found on the Junk Charts blog. This probably ought to be a bar plot, but since the y-axis doesn't begin at 0, it suggests that maybe the BBC was aiming for a dot plot. In which case, is the height represented by the top of the head or the centre of the head? Using a picture of a man instead of a bar makes things harder to understand, not easier. This example was created by the Fox News TV channel and found by Media Matters for America. You can see some familiar problems with the bar plot, like the y-axis not including 0, distorting the relative heights of the bars. Also notice that the time periods have been arbitrarily limited to October to April, omitting what happened between May and September each year. Let's focus on the skeuomorphic elements of the plot. There's a shadow across the panel of the plot, which adds no value, but since it travels upwards and to the right, it gives a subconscious signal that numbers are increasing. The bars also have been given a slight depth to them. The 3D aspect makes it harder to There are two basic measures of how good your data visualization is. The first measure is how many insights can the reader get from your plot. For far too many plots, the answer is 0. In this video, we'll look at some ways to avoid that situation. The second measure is how quickly the reader will get those insights. If your plot is being presented in a meeting, you might reasonably expect your audience to concentrate on your plot for 20 seconds. Often, you need to get your message across quickly. Chart junk refers to anything in the plot that makes it harder for the reader to get insight into the data. We'll look at some common problems in the following slides. One term that's less well known is skeuomorphism. That means adding things that happen in the real world to virtual objects. For example, you could add shadows to bars in a bar plot. Here's an example from the BBC TV network, found on the Junk Charts blog. This probably ought to be a bar plot, but since the y-axis doesn't begin at 0, it suggests that maybe the BBC was aiming for a dot plot. In which case, is the height represented by the top of the head or the centre of the head? Using a picture of a man instead of a bar makes things harder to understand, not easier. This example was created by the Fox News TV channel and found by Media Matters for America. You can see some familiar problems with the bar plot, like the y-axis not including 0, distorting the relative heights of the bars. Also notice that the time periods have been arbitrarily limited to October to April, omitting what happened between May and September each year. Let's focus on the skeuomorphic elements of the plot. There's a shadow across the panel of the plot, which adds no value, but since it travels upwards and to the right, it gives a subconscious signal that numbers are increasing. The bars also have been given a slight depth to them. The 3D aspect makes it harder to accurately judge where they lie against the y-axis, so the bar heights have to be written in text to compensate. By stripping away all the junk, the data is easier to see. This plot was found on the Data is Ugly subreddit and has many problems. Try pausing the video and counting the issues you can find. Let's concentrate on the unnecessary use of 3D perspective. Bar plots are inherently two-dimensional. You have categories on one axis and a continuous variable on the other axis. By making bars three-dimensional, you don't provide additional information, but simply make it harder to judge the lengths of bars. A 2D bar plot is easier to read, although one category label is missing and the percentages don't add up to 100, so it's unclear what the y-axis represents. Here's another plot from Data is Ugly, showing seats in the German Federal Council. There are 16 states and several political parties. Parties typically have to enter into a power-sharing coalition to get seats in each state. Each political party has a colour associated with their brand. CDU is black, SPD is red, Grüne is green, and so on. Each state on the map, or slice of pie plot, has the colour of the party which won the most votes, and stripes coloured by the other parties sharing power. The problem is that the plot is just too ugly to look at, so no one can get any insights from it. In general, stripes or other forms of hatching should be avoided in plots because they're just plain difficult to stare at. One Reddit user tried to improve the plot, as shown on the right. By removing the hatching, it's much nicer to look at the plot. Let's go to war on chart junk.
Mali lahat. So, ibig sabihin, access labels. 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 Yay, only 20%. Because I'm already sleepy. So for the multiple plots, sometimes the data set is so complex that it takes several plots to explore properly. Rather than trying to find a single perfect plot that captures all the insights, we can combine several plots into a report, or if we want to have fun, a dashboard. Antok na antok na. So here we can see the German Federal Council, because I don't know how to read the Bund General Council. Sits dataset in a dashboard of 3 plots. In the bi-party plots, values are colored according to each party's marketing brand color. The level of transparency is based on power. The primary party in a coalition is fully opaque. Secondary parties are slightly transparent, and tertiary parties are very transparent. So explore the dashboard and examine which statement is false. The coalition with the most seats is SPD plus CDU, which is false. It's true. Okay, the Green Party have more seats as the secondary party in a coalition than any other party. It's also true. The SPD has more seats. SPD what? SPD has more seats as the tertiary party in a coalition than any other party.
Well done. You've seen a lot of data visualizations now. In Chapter 1, you learned that histograms are excellent for showing the distribution of a continuous variable, and that box plots can compactly show the distributions of lots of continuous variables. In Chapter 2, you saw that scatter plots can show the relationship between two continuous variables, and that line plots are great for showing trends over time. You also saw that bar plots show counts or proportions split by categories, and that dot plots will do the same, but allow for logarithmic scales and showing multiple metrics at once. In Chapter 3, you saw that using colours or multiple panels are often the best way to add a third dimension to your plot, since 3D plots are hard to interpret. You also learned that there are 3 types of colour scale: qualitative, sequential, and diverging. For cases where you need to analyse many variables at once, you saw 3 types of plots. Pair plots show relationships between each pair of variables. Correlation heat maps show related variables, and parallel coordinates plots show patterns across many variables. In Chapter 4, you learned that plots with polar coordinates are usually a bad idea, but they have niche uses when data is cyclical, like a time of day. You also learned that using dual axes is almost always misleading, and that minimalism is a good idea. You should eliminate anything from the plot that distracts from interpretations. If you're interested in learning more about data visualization, you can take courses on the R package ggplot2, which was used to create the plots in this course, or on business intelligence tools like Tableau, or Python packages like Matplotlib and Seaborn. Happy learning!
Statistics. Understanding. Back to dashboard.
Hi, and welcome. My name is George, and I'll be your host as we discover the core concepts
is